What do we know here? That's what's important. Stuff that's happening. Show that if the point representing W lies on the real axis. W lies on the real axis. We want to show that Z lies on a line, but we don't know which line, so that's not what we want. What we know is that W is on the real axis. Okay, so don't know over here, but going to the real axis here. So we write down what we know. We can write this in two different ways, can't we? We could write V equals 0, or we could write, what's the other way of doing it? We could treat it as the perpendicular bisector of I and minus I, and we could say W minus I equals W plus I. That's what we know. We're going to sub in. W is Z plus 2 over Z plus I. I'm going to do this one first because it's easier. Oops, minus I, Z plus 2 over Z plus I, plus I, plus I. Okay, Z plus 2 minus I, Z plus I. What is going on when I write plus I? Plus I all over Z plus I equals Z plus 2 plus I, Z plus I over Z plus I. Okay, usual tricks. Modulus, stop modulus at the bottom separately and then cancel the moduluses off the bottom. I'll do it in blue so you can see. So modulus, 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 cancel, cancel. Nice little step. I'll just give myself some room. So what have we now got? Z plus 2 minus IZ minus I squared equals Z plus 2 plus IZ minus I squared, so plus 1. Let's tidy it up a bit. Z. How many Z's have I got? 1 minus I plus 2 minus 1 plus 1. Had to think about that. Z. How many have I got? 1 plus I plus 2 plus 1 plus 3. Okay, I need to pull these numbers out. This is the standard thing that we need to do here. We just want Z. Z, Z, Z. Don't want that there, so we're going to pull this out as a common. It's not really common, but we'll make it a common factor. 1 minus I, lots of Z plus 1 over 1 minus I, modulus, equals 1 plus I, Z plus 3 over 1 plus I. And then we've got moduluses around them. Okay, let's do the thing where we make modulus of the product as product of moduluses, like that. And then we can work out what the modulus of these two little bits here is. 1 minus I and 1 plus I. Well, 1 minus I is here on the Argand diagram, and this distance here must be root 2 because it's 1 across and 1 down. What about 1 plus I? 1 plus I is here, across 1, up 1. So this again must be root 2, this modulus. 1 squared plus 1 squared square rooted. So this is root 2, this is root 2, and we can divide both sides by root 2. Let's give ourselves a bit more room. It's all simplifying out quite nicely now, isn't it? What have we got? Z plus 1 over 1 minus I, modulus, equals Z plus 3 over 1 plus I. Now I can see straight away, maybe I should write, instead of plus, minus, minus, because it always needs to be a minus in there. Like that. I can see I've got a perpendicular bisector. It's the perpendicular bisector of minus 1 over 1 minus I and minus 3 over 1 plus I. What was I trying to do? I was trying to show that they lie on a straight line, and I have shown that they lie on a straight line. I haven't actually got the exact points. If I wanted to, if I could be bothered, I would rationalise the denominator, and then find the exact points in Cartesian form. But I can't be bothered, I have shown that it lies on a straight line. Right, now for the other way, V equals 0. So we know about W, so let's start by writing what W is, because I know something about W, so that's what I start with. But because I've got a domain, V is 0, well it's a range really, because it's to do with W, but a restriction in Cartesian form, in component form, in terms of u and v, I need to get my z's in terms of x and y. I need to sub in x plus I, y. And then everything can be in component form. So let's do that. W equals x plus I, y plus 2. x plus I, y plus I. Okay, I'm going to have to realise or rationalise the denominator here. So the bottom there is x plus I, y plus 1. So the conjugate is x minus I, y plus 1. And that's what I'm going to have on the top and the bottom. And on the bottom, when I multiply them together, I'll get x squared plus y plus 1 squared. And on the top, x plus 2, there's my real bit, plus iy multiplied by x minus I, y plus 1 on the top. Whew, it looks a bit disgusting, but I'm sure it'll all work out. I think I prefer the loci way, but I shall persevere. Okay, expanding out. We have x plus 2, minus I, y plus 1, x plus 2, plus I, y, x, minus I squared y, y plus 1. And I'm going nice and slowly so I don't make any mistakes. Or, at least, I'm less likely to make any mistakes. Okay, let's organise this into, don't forget what we're going for is w equals something plus I something, because this bit is u and this bit is v, and we know about v is naught. So w is x plus 2, that's real, and then minus I squared, so plus y plus 1 over x squared plus y plus 1 squared, plus, we definitely need a plus there, plus I, okay, how much imaginary have I got? Yx minus y plus 1 x plus 2 over x squared plus y plus 1 squared. Okay, that's looking good. And I know that this is u, w is u plus I, v, and v is naught, because I know that w lies on the real axis. So this is 0, so I can make that into a separate equation. Goes there. So what did that give me? Yx minus y plus 1 x plus 2 all over x squared plus y plus 1 squared equals naught. So obviously I can multiply both sides by the bottom and expand out the top. What would that give me? Yx minus yx plus x plus 2y plus 2 equals naught. So the yx will cancel the yx, leaving me with minus x minus 2y minus 2 is 0, or multiplying through by minus 1. We could have x plus 2y plus 2 is naught. So that is a straight line, obviously, and in a way that was better than using the loci method, because I have got the actual equation of the line, whereas before I just knew it was the perpendicular bisector of two random points. But on the other hand, I had to do all of this stuff with x's and y's, which was a bit tricky. Okay, let's try part B. What do we know now? The point representing W lies on the imaginary axis now. The imaginary axis. Okay, so again, don't know anything about Z, but we do know about W. Again, two ways of explaining what this is. We could use, well, this is U and this is V, so we could say that U is naught, or we could treat it as a perpendicular bisector of, say, minus 1 and 1, so W minus 1 equals W plus 1. Now, you saw just now how messy this one can get. If you've got to do that method, you've got to do that method, but if we can avoid component form, then usually that is easier. The other reason that I would go for this is look at what we're actually going for. Z plus 1 plus a half I is root 5 over 2. That's what we want to end up with, and that's got modulus signs around it. So if we start with them, I think we're going to find it more easy to get to here. So this time I'm not going to bother with that one. I'm just going to go with the modulus form. So subbing in W, Z plus 2 over Z plus I minus 1, which I'll write in the form Z plus I over Z plus I, equals W, subbing in W, Z plus 2 over Z plus I plus Z plus I over Z plus I, equals Z plus 2 minus Z minus I over Z plus I, modulus, why did I write equals there? I meant therefore. Therefore this equals Z z plus 2 plus z plus I over z plus I. Usual trick. So the modulus of a fraction is the modulus of the top over the modulus of the bottom. So we can do that, and then we can cancel the bottoms because they're the same. That gives us z minus z, 2 minus I, equals, what have we got here? 2z plus 2 plus I. Okay, well, 2 minus I, where does that live on an Argand diagram? 2 across, 1 down. What's this distance here, this modulus? So that's 2 squared. 2 squared plus 1 squared rooted root 5. Yay, we've got our root 5. That's a good sign. So this is root 5. On the right-hand side, we must pull this 2 out. We can't have anything in front of that z. So the 2 is going to come out. So it will be 2 lots of z plus 1 plus I over 2. Wait. I over 2. Like that. Oh, that's what I want. Good. Modulus of the whole thing. And then the modulus of the product is the product of the moduluses. So mod 2 mod z plus I plus a half I. And then the modulus of 2 is just 2, obviously, because it lives there. So the modulus of 2 is 2. Dividing both sides by 2, we get what we wanted. Front half room, but we get exactly what we wanted, which was z plus 1 plus half I. Modulus is root 5 over 2. There we go. Not too bad, I don't think. If you wanted, for fun, I'd be very impressed if you did this. Depends if you want to impress me. Have a go at doing it that way. Just see if you can do it.